Hello everyone. Today I have this book physics in Cambridge course book, yeah, physics Cambridge International S.A level from David Seng. Today I'm going to share you how to solve some question about S.H.M. S.H.M is simple harmonic motion. Here we go. This one. But before we continue, don't forget to subscribe, subscribe to this channel. Thank you very much who already subscribed. Okay, go to number 16. A mass secure at an offspring move with S.H.M simple harmonic motion. The frequency motion is 1.4 Hz. Question A. Write an equation of the form A minus or negative omega square x to show how the acceleration of the mass depends on the displacement. Okay, actually the acceleration is A. The acceleration is A, and then the displacement is x. Acceleration. So this is negative omega square x. This is acceleration, and this is displacement. Sorry. So we have omega. Omega is 2 pi over t, or 2 pi times f. So because we have frequency, we change frequency to 1.4. So omega equals to 2 pi times 1.4. So this is 2.8 pi, right? So we have a function A as a negative 2.8 pi and then square x. 2.8 square means with his calculator first. 2.8 square 7.84. Oh, sorry. This negative 7.84 pi square x. That's it. So this is the equation 1. Or maybe if we change pi into 3.14. So same thing with we calculate first 3.4. This has become 24.61. So this has become A means negative 24.61 and blah blah, x. So this. So acceleration depends by displacement. By constant is 24.6. Okay, done. Let's check question B. Sorry, I will move this into. Sorry. Oh my god. Wait. Here. You can see this. Question B. Yes. Let's check it. about question B, after we have uh, a acceleration as a function of displacement, yeah. B, calculate the acceleration of the mass when its displacement 0.05 meter from the equilibrium position. Okay, so B is, we have x is 0.050 meter. So since we have a is negative, 24.6, yeah, x, so this is something 24.6 times 0.050, yeah. Okay, calculate first. 0.05, oh, 1.23. This is about negative 1.23, yeah, in meter second minus 2. So this is the acceleration 1 when the position, yeah, when the position from the equilibrium is 0.050 meter. That's it. Okay, now what about question 17? Sorry. Question 17 is, short pendulum oscillate with S.H.M, simple harmonic motion, such that acceleration A in meter second power minus 2 is related to its displacement x in meter by equation A is negative 300x. Yeah, determine the frequency of the oscillation. Okay, you know it is when we have acceleration is negative omega square x, yeah. So from this, yeah, we can say the omega is 300, right? Yeah, because negative 300x omega square, sorry. Omega is because we need to determine the frequency, omega is 2 pi f, yeah, square equals to 300. So f means root 300 divided with 2 pi, yeah. Oh, sorry. Frequency means root of 300 divided 2 pi, yeah. That's it. Root of 300 is oh my god, root 300, I think about 17 point, this is about 17.32 and then divided, is it, yeah. So divided by 6.2, 6.28 equals 2.76, yeah, this is about 2.76 in hertz, yeah, that's it. Okay, this one, yeah, we start from the equation that A is equal to negative 300x, yeah, means negative 300 equal something with omega square, yeah. Omega square is 2 pi f, yeah. Since we need to find the frequency, so we change omega into 2 pi f. But if we need period, so we change into 2 pi over t, yeah. So frequency means root of 300 divided 2 pi. and then we get this is about 2.76 hertz. That's it. Okay, go to the number 18. Don't forget to subscribe this channel. Yeah. Oh, what about this? I think here. What was here? The pendulum of grandfather clock swing from one side to the other in 1.0 second. The amplitude of the oscillation is 12 centimeter. Okay, here. Amplitude, yeah. Number 18, we have period 1.00 second, and then amplitude we have 12 centimeter. Question A is calculate the period of its motion from one side to other in, oh sorry, this is not period, yeah, this is a half period. Sorry, this is about t, yeah, because swing from one side to other in 1 second, so period means 2 times of 1.0, yeah, this is equal to 2.00 second. The frequency, sorry, this is question A, yeah. Oh. Frequency is 1 over t, 1 over 2 equals to a half, yeah, hertz. Yeah, that's it. Then the angular frequency, yeah, angular frequency is 2 pi over t, yeah, 2 pi over 2, yeah, so same thing equals to pi, yeah, or 3.14 radian second minus 1, yeah, that's it. Then write an equation of the form A negative omega square x to show how acceleration of the pendulum bob depends on the displacement. Oh, okay, we only include this one, yeah. So this is something with on the big question is because A negative omega square x, omega we have pi or 3.14, yeah, pi square, so 3.14 square x, 3.14 is square is times 3. This is about 9.8596, yeah, maybe 9.86, negative 9.86 x, yeah. So this is the equation of acceleration depends by displacement. So what about C and D? C and D is here. Calculate the maximum speed of the pendulum bob. Maximum speed, yeah, maximum speed is wait. We have maximum speed of oscillation. Oh, this one, yeah. X equals to 0 with the speed it's maximum. So VO equals to omega, or yeah, CVO equals to omega X. Oh, omega we have 3.14, and then X is maximum when the position is nodal oscillation is 12, yeah. Wait. Oh yes, correct. This is x equals 12 centimeter. So this is equals to 3.14 times 12, 37.7. This is about 37.7 in centimeter second minus 1. Yeah. Why? Because x, or maximum displacement or amplitude, is 12 centimeter. Okay, calculate the speed of pop when its displacement 6 centimeter. We use this one, yeah. Use this one. So V equals to omega times root of xo square minus x, yeah, square. So omega is pi, or 3.14, and then xo is 12 square, x is 6 square, yeah. So this is about 3.14 times root 144 minus 36. This is this is about root of 108. So root of 108 10.3, and then times 3.32, yeah, 0.6. This is about 32.6, yeah, in centimeter second minus 2, yeah, because still in centimeter. Okay, that's it, yeah. I hope you understand about this, yeah. Then we still have one question. Let's check. The last question is about proof the equation, yeah. 19 here. A trolley of mass m is fixed to end the spring. The spring can be compressed and extended. The spring has force constant K. The other end of the spring is attached to a vertical wall. The trolley lies on the smooth horizontal table. The trolley oscillates when it's displaced from equilibrium position. So that the motion oscillation trolley is simple harmonic motion. Yeah, because trolley oscillate when the display from the equilibrium position, so swing is what we call it here. They have moved from the maximum position to the equilibrium, and then into the maximum position in different direction. Yeah, like they have sinusoidal function, yeah, from the equilibrium position, maximum position in one side into other side, yeah. So when they have moved back periodically, so they called as the simple harmonic motion. Then what about question B? So we need to prove this. T equals to pi times root of m over k. Wow. How do we solve? Yeah, we use f equals f equals to ma. Ma equals to negative m omega square x. Ning kelas
lagi ngomong ya?
iya. Since we know Newton's second law is F equals to ma, so a we change into omega square times x, yeah. As you know, the acceleration, same thing with negative omega square times x. So from this we will change into what? Oh, spring constant. Oh, we change kx. This is equals to negative m omega square x here. So this is negative also, yeah. Why? Because the direction is opposite. Then kx equals to m omega square. Yeah. Sorry, x we cancel yeah, this one. Yeah. So omega is 2 pi over t square equals to k over m. So we flip t over 2 pi square equals to m over k. Yeah. T over 2 pi equals to root m over k. So t equals to 2 pi root m over k. This one. We start from Hooke's law, yeah, that force equals to k times x. Yeah, that's it. Thank you very much for watching this video. Don't forget to subscribe, yeah. Thank you.